My name is Mike, and I'm the CTO of Dataprophet, and I've got some really exciting stuff that I would like to share with you today. To talk a little bit about the business, we started off in 2014, and we have this belief about machine learning. Machine learning is this really exciting set of mathematical tools that have been gaining popularity and notoriety, and we find a lot of folk who are peddling the stuff, but then reducing themselves to, or reducing the delivery to just that standard statistical description. So the core hard ethos behind Dataprophet is really good machine learning. Over these past 5 years, we've been building up our team. We now sit just over 35 with a core technical competency team of around 20 folk. So this means that our developers and our data scientists are still in the majority, and we've got to hold back the forces for as long as possible. And I'm going to talk a little bit about the story, but we are all about process control. And it's not about the closed loop control systems, it's about that next hard level. Given something really super complicated, how do you take an action now that minimizes risk and loss later? And this isn't going to be a sort of risk chart where you say that on some axis you have some consequence and on some other one you have some likelihood. It's a way more complicated approach than that, and it gives a lot more value and better insight into your system. We've got some really amazing case studies that we can talk about, particularly the fact that we can take this huge, mature business that has been producing engine blocks for decades and bring them down to 0% scrap. I'm going to unpack this one in detail particularly, or how we can go to Daimler globally, who has been doing stud welding and been throwing experts from universities around the world at the stud welding problem, walk in as machine learning experts, not as welding experts, and reduce the number of defects by half. And the implication here on an assembly line is that when a stud weld fails, you've got to take the entire vehicle off the line to do the repair. You've got to get a technician in there with a TIG welding equipment to actually do that fix. And at the same time, all of that just-in-time logistical sequencing gets wrecked because that vehicle is no longer in the queue. The cost of non-quality cascades through the system, where you're now suddenly installing a tire inflator for the wrong version because it hasn't been pulled from the production queue. Just think about that knock-on series of effects. You reduce that by half. That's half the number of cars that are being scrapped. I mean, it's double the throughput in terms of your loss. It's quite an exciting impact that we've had. So I'm here to talk about two main components. I'm going to unpack the first in exquisite detail, and the second I'm just going to touch upon. The first part of the problem is how do you optimize a hyper-complex process that has many steps in it, that is mature, that you've had businesses looking at for years. And then the second solution that we offer was born out of the sort of perceived, or out of the failure of quality reporting. So you've got a nice big industrial process, and you've got folk who are doing infrequent batch sampling at the end of the game, and they're kind of like driving down the highway, looking in the rearview mirror with smudged sunglasses on, right? It's not fun if you're trying to drive that vehicle. And so by doing better quality control, you can help them get a better sense of that system. To talk a little bit about some of the work, it's a crazy ride. Traveling almost every other week, primarily into Europe, into the automobile sector. We've got Volkswagen, Daimler, we've done work for BMW up here. We've done work for Atlantis Foundries down on the Western Cape coast. We have partners in Brazil and in Germany, that's Portec and Kitron. We have a sinter metal company. The sintering process is where you take a metal powder and you squeeze it and you bake it and then you squeeze it again to get a very exotic shape. So it's heavy industry. We have Goodall, which is a continuous long steel process. This is where you have these long billets used in the manufacture of, or the construction of high-rise building, the steel and concrete. Those billets get made on these sort of systems. And all of these folk are optimizing their processes with Omni. So the story starts. We're doing machine learning. We've got a consulting team out, and we're looking at a variety of problems. Everything from scheduling adverts for maximum impact on the maximum sort of revenue spend on advertising, for maximum impact on the business. We're doing some credit score risk modeling. We're doing some category management for retailers. And the CEO of Atlantis Foundries walks into my office, and that week he had had his worst historic scrap rate, something close to 20%. What was happening is he casts these engine blocks, He pours half a ton of molten metal into a big, very complicated mold. It cools. They do a little bit of surface machining. They ship it off to Mannheim in Germany, where they get some deeper machining, and they find these subsurface defects. It's like a little bubble. This defect causes the entire block to get scrapped. And so you've got this really complicated process. You're putting a whole bunch of energy into it. You're putting a whole bunch of labor into it. You're incurring the logistics costs, only to have it arrive at your customer and get hit with a penalty. And so that penalty, in fact, meant that there was no revenue that month. The penalty was so large. And so this is what a foundry process looks like. Everything from incoming material that you can't control, which is sand from a sand mine near the Atlantis dunes, through to a mixture of various metals to make the right steel alloy for this engine block. You're combining sands, you're adding various epoxy resins, you're curing these with gases, you're adding bentonite, coal dust, moisture to the sand, you're mixing it all together, you're squeezing it into a shape, you get this single pour event, you've got to cool this block down perfectly, you're allowed to do a little bit of like touching up in case it hasn't filled a spot. You do some level of inspection, but it's a very rough product, so it hasn't been finished, so your inspection isn't that great, and eventually you ship this off, only to have this defect come back later. And at every stage in your process, you're making a measurement. So you're measuring, for example, the grain size distribution of the incoming sand from the mine. You're measuring the amount of coal dust and bentonite that you're adding to the mold. You're building in some sort of traceability, you're measuring the kind of metal that you're getting, and you've got experts at every step of this process. Your scrap rate goes up, so you call a shop floor meeting. You get all of these guys around the table, and it's either one of two things. It's either that I understand my process, therefore I must make the change and improve it, or it's the blame game. It's not my fault, guys. I'm not changing anything. In fact, the defect happened because you did the following. So you've got all this sort of like industrial politics that get in the way of actually getting to the root cause. With the second problem of this being so complicated that your metal pouring expert doesn't have competence, just can't maintain competence in sand processing. We wouldn't expect them to, right? You've got an engineer who's dedicated to understanding metal, and he does a really great job of that, and he's controlling his process to the very best of his ability there. And you've got the same story with the sand guy, where he's making all of these adjustments and changes. And you could almost have the stack up, where the sand guy makes a bunch of corrections that makes the metal pouring guy's job impossible, no matter how good he is, or even vice versa. And so even though the communication can't happen, you've got the data that tells the story. And you've got the data that tells this decades of this story. And so we went off to his site, we pulled this data, we built some models. This was super ninja. We were really just making machine learning models because we thought that was fun, and it is. We came up with some results where we started predicting whether or not an engine block would contain a defect. And as a result of this model, he stopped shipping blocks that we said we believed contained defects. So suddenly what happened is the number of defects that were arriving at his customer went down, but his internal scrap costs went right up. Customer wasn't that happy, because it turns out that they use the penalties to modulate the contract value. So there were a bunch of German guys coming in saying, "What's going on? 999," which was quite exciting. And the problem gets posed to us, what do I do now to minimize this internal scrap rate? So you've solved my customer interface problem, and the quality of my product is much better, and this is really exciting. But you've got to help me stop making the scrap, because my business, I'm no longer incurring the penalties, but I'm still incurring all of these scrap costs. And so we had to come up with some kind of math that would allow us to say, well, you make this small change to one of these 1,500 odd parameters that you can twiddle, that's going to have an impact on quality. And right now, these are the 5 very best things for you to do. It's not trivial, right? It's quite, and I'm going to unpack exactly how we get to that. I want to talk a little bit about the kind of complicated environments, data environments, that you find at mature businesses. By very definition, these guys have evolved. They've started out with something quite small. You've had this initial process work, and then they've modernized this part of the factory. Why? Because that's just the right amount of capital that they could afford this financial year or this investment cycle. And then the next part of the factory gets upgraded. And in that time between these investment cycles, you've had a whole new branch of technology. And so you've got the entire range of industrial equipment. PLCs from the early 80s right through to modern SCS7 control systems, which are super advanced and trivial to connect to. But the whole collection of these devices tells the production story. So you've got to pull data from all of this. So you can do a bunch of things. You can go to the client and you can say, you've got to upgrade your old control system. This is the capital cost, and it's going to take you this much time before you're going to realize any value. And I kind of go, well, my system's working good enough. I don't want to invest that. The return on investment isn't there. Or we can innovate, and we can take that burden upon ourselves and say, well, it doesn't actually matter. We're going to do the upliftment. We've got the experts who can build the connectors to all of these data systems, which is fantastic. We're going to create this holistic view for you. And the very first time that Atlantis Foundries had ever seen the full production story for a single engine block was when I delivered my unified view that I was predicting upon, which is quite a story, because now you can say this block with this defect had this set of conditions. So a lot of hard work, but we got that right, and I think that's the critical thing. It's not about taking data that you don't have yet. Chances are, if you're controlling it, you're measuring it. You've just got to do the heavy lifting to get there, which makes for a really exciting landscape. You've got these things called historians, which are just really fancy databases. You've got direct from the machine, usually like some sort of Ethernet interface with some IP connection on top of it, plus some proprietary protocol because the guy wanted to create relevance for his piece of work at the OEM. You've got a proliferation of IoT sensors with various different standards. There's been some work towards harmonization of these standards, but it doesn't matter. They're still making a good measurement, and I can ingest that data. But you've got these different update frequencies, you've got these different sampling frequencies, you've got these different data stores, and you've got to be able to handle this sort of dynamicism in the data space. So this is our solution, and we really bled out of our eyeballs to get to this, but it's had some really robust engineering debate on this. And I'm going to talk you through, I'm going to unpack exactly how we put this together. I'm going to start with the user, because I think that's super important. A rapidly responding, polished user interface is one of the key components about the user experience. It's about making interfacing with the data as frictionless as possible. So to do so, we serve our React app through CloudFront, and this makes it really responsive. And if you think about what our global customers look like, we can just deploy this to the relative availability zones that make this really nice and quick and fast. This front end then connects through to an API, through which the data are served. So there's a clear separation between web app machinery and data serving machinery. This is quite important because when you've got a whole bunch of users, the actual load for the web app is quite small, but you've really got to be able to deliver this data quite quickly. You've got to scale it as your user demand varies. And we use some of the AWS infrastructure around that. So it's elastic load balancing with an autoscaler. Then we're going to talk a little bit about the data. So you've got all of these machines. They're going to be doing whatever within your process. These are writing to some sort of interface. This really doesn't matter. There's generally a published API specification, and you've got to be able to have guys who have the tenacity to sit down and either build their own connector. It takes time, but it's not impossible. But generally, you find that there's quite a lot of support for some of the more modern things out there. And this isn't the end of the world. We run this on an Airflow pipeline. So we use a series of directed acyclic graphs, the DAGs, and we scale these out through a pipeline, so it just hammers out a whole bunch of celery workers. And again, this scales as various data sources become available, or whatever the schedule is that's necessary. So depending, user load and data ingest load are entirely decoupled. So you can have some stuff going on on your back end, you can have some stuff going on in the front end, and the two aren't going to affect each other depending on that load. And we're pushing this data. We have some temporary ingest, which we found to be quite important, because a lot of customers we find would far rather push data at you on some schedule that they can manage. And so we just provide an S3 bucket that they can push that into. But our pipeline workers are also able to reach out directly using the connectors that we've engineered to ingest that data. Then comes the real super hard part of what we do. This is the machine learning part. I'm going to unpack some of that detail. But it's in this space that we're training some unsupervised model. We're learning some representation of the production process, and we're finding some region in this unsupervised landscape that describes the optimal set of conditions. We're going to talk a little bit about some of them about the models. And key to prescribing input to the customer is being able to tell them, of the 1,500 things that you can go and fix, the 5 things, i.e. you've got a limited capacity, the 5 things that you've got to go and change now are the following, which means that I've got to go and load my model. I've got to do some sort of traversal through the latent space. I'll unpack all of this in a sec. Some sort of traversal, we've got to say the greatest impact is across these 5 variables, and these are the 5 changes you make, which means that I've got to, in the time of the request, I've got to pull out my model, which is sort of quite a cute little TensorFlow device, wrapped up in some container. We use your container service for that, and then we actually serve that model for the inference part, which forms part of the input to the API. So at the same time that we are shipping time-wise process data, we're running an inference on a TensorFlow model. Both got to arrive at the web app at the same time to serve some meaningful results. Fun. Right, so I think just a little bit about the work that our infrastructure team does. We all do this declarative provisioning. We're using Terraform for that. We're getting the stuff out, the right set of applications in the right state onto these various instances using SaltStack. We're using your container registry for our model versioning and serving it. And it allows us to individually scale that inference capacity, which means that to get a new model or a new version of a model or to update and retrain doesn't incur any sort of burden on the other side of the user. All of this is seamless to them. Okay, so I've spoken a lot about the back-end stuff, but when I'm saying models, what are we really doing? And I'm just going to spend a bit of time on that because I think that machine learning is amazing and I want to share this cool stuff with you. We take this machine data, we've now pivoted it to talk on a per product basis, and we've done some dimensionality reduction where we're learning a manifold. This manifold has almost infinite surface area, which means that you can't do any direct measurement on this space. You can't say that distance actually means anything. You just know that there is distance, and therefore you've got these separate encodings. Each point here represents all of the conditions that led to the birth of a single engine block. And you can see that you've got a bunch of scattershot on the bottom left, and the presence of this scattershot corresponds with high variance in the reported or the recorded scrap rate of the production system. And you notice that as the sort of majority of components produced moves up into this area, that there's a small reduction in the recorded defect rate. So the blue represents a historical production capacity on this manifold, on this machine-learned manifold. So if I can somehow direct my operators to make small adjustments to move through this latent space to the ideal region, I expect to see a reduction in my scrap rate. The other thing is if I can get rid of this scattershot, this is when the sand guy does a whole bunch of things to the one side of the extreme, and the molten metal guy does a whole bunch of other stuff on the other side of the extreme. You get this tolerance stack up, and that's what the scattershot is, that the variance in my defect rate should go down as well. So we did exactly this. We provide this guidance to their production team. It takes a few weeks to get them to the ideal zone. They start producing that zone, and the scrap and rework goes to 0. So suddenly that internal scrap rate doesn't exist anymore. And now I have an awkward conversation with the CEO. It went along the lines of, I've been doing this for 40 years, how did you do this? It was amazing, a lot of fun. And it doesn't always go right. And I think that this is the next part about machine learning, is you can't just blindly throw an algorithm and close your eyes and expect the results to be good. You can train up some model, you can have some amazing validation loss. And the reality is that you've got this terrible effect known as posterior collapse, which is when the ability for your decoder, it far exceeds the ability of the manifold to describe the problem. So you can think of it like two opera singers, and one opera singer is singing a lot louder than the other, and so kind of everyone focuses on them, when in fact it's all about that teamwork. This is the same set of data, two different iterations of model training. One, we've actually learned a quality representation. So here the color represents the amount of an impurity. 0 is better. We find that we have this fantastic region where this particular impurity no longer exists. In other words, if you do your process in this manner, you no longer get this impurity. And here we've entirely failed to learn any representation. And so it's about getting that model right. And so even though we can make the system scale beautifully, we've got to have a real good team of data scientists and process engineers to get the right sort of story told through the data. So it's a little bit of a caveat around AI and ML. It's not, you can't just close your eyes and throw data at a bucketed model. It's not going to give you anything you go to the bank on.
How do you know when it's wrong or right?
This is the qualitative inspection. So it's there's some visual inspection. This overlay is obviously the quality, and here it's separated. And the standing joke in the office is when you're training a model, you suffer separation anxiety. This is it in live action. So there's our dashboard that we provide to the operators. This is at Atlantis Foundries. If anyone would like to go and visit and have a look at this, we have a wonderful relationship with them. So I'd love to, if you would, just reach out to me and we can organize a visit that you can go and have a look. The way that this war room operates is that you have a bunch of process engineers who are monitoring process for compliance. You've got this prescription directing their actions, and they're radioing these effects through to the operators with a radio network. So they're having a conversation, guys, you've got to increase the amount of chromium that you're adding to your alloy mix. Or your sand, you've got to increase the amount of moisture that you're adding. These prescriptions are described as follows. This is the single most important thing that you've got to go and change on your process. This identifier has direct relevance to the operator. They know what this parlance, this is part of their control system. This is the ideal range. This is their current production value. And at the moment, this is the most important ranked device. In other words, for the greatest impact, you go and change this thing now, and you reduce 0.42 to something less than 0.36, but keep it above 0.33. There's a little bit of the time series data. This is what we're shipping out of our API. So all of this data is getting out of that API onto the web app front end. The other thing that we found, and this speaks to a little bit of the human part of the problem, is you've got to tell guys what they're doing right. Because often we forget too quickly that you've broken this, go and fix this. We forget to say, but hang on, you're actually doing a really good job on this parameter. Just keep an eye on it. We discovered that by including this within our ranking, we find total compliance or ability to accept the prescriptions that we're generating to be a whole bunch more accepted by the operators. And so I think that there's a soft word here. It's about keeping humans in the loop and engineering a solution for people. I think that there's another comment, and that's about, again, speaking to mature processes. We generate control plans, and you've got to do so in the way that folk are used to seeing. Well, a lot of the businesses that we engage with have existing statistical process control, and they've got to make these changes, and they're very sensitive to the sort of change process. So here it's trivial, it's just generating a report in exactly the same look and feel as the folk are used to. Nothing changes, but suddenly you're hitting all your production targets. It's fantastic. And then obviously you find that project sponsors want to get a better view upon their entire system. So we do some aggregate reporting for them as well at a higher level. We're also breaking apart sections of the plant. So we're giving foremen of sections of the plant just a view across their section. This speaks to a lot of the ownership problem. And here you've now got to do this latent traversal, but just bear in mind a subset of controllable parameters. So it makes the problem even harder. It's okay, we can deal. So all of this at quite a high level. You can see the infrastructure that we've put together to deal with it. In summary, we're pulling in all the machine data. We're doing the ETL and warehousing. We're doing the heavy lifting. There's no conversation around, do you need a data lake? Or do you need some sort of system to provision? We handle that. I think that's really important. Folk these days are pretty fatigued around that conversation. You've just got to take that problem off their hands. It's not even a point for discussion. You've got to handle the generation of reports and prescriptions. The aggregation is necessary. And you've got to automate that report feedback in the tempo of the organization. You've got to empower process owners by keeping them in the loop. And on all of this, you've got to be able to generate your first results super quickly, which means time from arrival to generating your first prescriptions got to be in the order of a month. You're not finding folk with patients much longer than that. And again, this is a problem that we rise to. Again, at the same level, but across multiple sites. So one of our clients produce multiple products through a global organization. They want one dashboard. Easy as, right? You've got your own airflow pipeline dealing with data from every site. It can be a total different update frequencies, total different amounts of sampling intervals, the works. Suck that through into our system and custom dashboards for everyone without incurring any additional debt on that processing. Make our model, and it's great, and it's good to go. So I think just in summary, a market product fit is super critical. You can overserve some industries. We've been pretty lucky. We found a bunch of folk who are desperate. You've got mature industries, they're cash producing, and they're under a lot of pressure to maintain the feasibility of their operations. A 1% improvement in yield means the entire world to these folk. You've got to architect for congruency, which means that these businesses have their own view upon data. You can't suddenly share data into the same database. You can't share models between clients. And you've got to be able to demonstrate that you're not going to be able to leak any of that information between these folk. And so the architecture has to take into account your customer's belief on how unique and how valuable their data is without compromising it. And I think that core to this, and I started my story with the user experience, it's about providing this frictionless way that's human sensitive, providing the input and the insights. Thanks.